In the previous module, we have noted that the Fourier transform tool can be used for both periodic as well as aperiodic signals. In this module, we are going to introduce the Fourier transform for discrete time signals. Now, the Fourier transform is specifically meant for aperiodic signals. However, if we allow the impulses, as we have seen in the previous module, if we allow the impulses that can be applied to the periodic signals as well, we are going to see the same thing for the discrete time signals in this module. Before going into the math, let us make an observation. We see that an aperiodic signal, that is x of n, is shown on the screen. Let it be defined for discrete samples, say from between n1 to n2. So we have here a simple aperiodic discrete time signal x of n. Now this discrete time aperiodic signal, let me write that this is a periodic signal. This aperiodic signal can be considered as being a part of a periodic signal whose period is infinite. What I mean by that is that this x of n can be thought of as a part of signal of xp of n, that is a periodic signal where its period is n, and let's suppose if this n, that is the period of this periodic signal, tends to infinite, then we may say that this periodic signal turns out to be this aperiodic signal x of n. That means this n, if somehow we try to make this as infinite, tending towards infinite, we would obtain the same signal, that is x of n. Along the same lines, we'll be doing the math and we'll be deriving the equation for the Fourier transform for discrete time signals, similar to what we have seen for the Fourier transform of continuous time signals. Let us do that. Now this xp of n, that is the periodic version of x of n, this being a discrete time periodic signal, is going to have the Fourier series representation. That means this xp of n can be represented with the help of discrete time Fourier series as follows. So this xp of n being periodic, xp of n using the discrete time Fourier series can be represented as summation ak, that are the Fourier series coefficients, into e power jk omega naught n, where this k is over an interval of n, where this capital N is nothing but the period of the periodic signal, that is defined as n equals to the period of this periodic signal under consideration, that is xp of n. And this omega is the fundamental frequency that is given by 2 pi by n. AKs are the Fourier series coefficients that are given by AK equals to 1 by n summation x p of n e power minus jk omega naught n. We know these equations, and these equations are the Fourier series representation. So these equations are the Fourier series representation, Fourier series representation of discrete time periodic signal, that is xp of n. Now our aim is to find the Fourier representation for this aperiodic signal, that is x of n, and we know that in order to make that, we have to make this n, that is a period, tending towards infinite. Now let's look at this equation here. This ak is 1 by n. Now the summation is again over a period of n, so So this small n is again over a period of n samples, just because after that the signal is going to repeat. Now this summation, that is over a period of n, we may take any period. So if you look at this figure here, if we have a look at this period, we may take, if the signal is periodic with the period of n, we may take the samples from say 0 to n minus 1, or I may take the sample from 1 to n. So that accounts for n samples. So we may take any n samples in the interval. So I would be choosing the interval that is convenient to me. So I'll be choosing the interval from say from, for example, from n minus n by 2 to n by 2, or I may choose anywhere in between. So I'll be choosing the interval such that a continuum of one period is obtained. As I said, we may choose any interval in which this signal is periodic. As the signal is periodic with n samples, I may choose from 0 to n minus 1, or I may choose from 1 to n, or I may choose from 2 to n plus 1, and so on. So I'll be choosing the period something like this. Say for example, between these samples. Now I'm doing that because it will be convenient to have a continuum of these samples. So these samples are available one after the other for one period, and therefore I'm choosing this interval. Like such, you may choose any interval. So this AK can be represented as AK equals to 1 by n summation over a period. As I said, I am choosing the period between these and this interval. So this interval, and you may see that the samples are non-zero only between n1 to n2. So I may choose the summation that is over a period of n from say n1 to n2, where n1 is the lower limit and n2 is the upper limit of this signal. Now this can be represented as equals to xp of n e power minus jk omega naught n. Now if you observe this equation here, you may see that we just have to take into consideration xp of n over a period. And you may see that if we look at the signal over a period, the signal is exactly equals to this signal over a period. So what I mean to say is that this signal here is exactly equals to this x of n over a period. So if I'm choosing a signal here, you may see that this interval, the summation, is over a period from n1 to n2, and this xp of n is exactly equals to x of n. So let me write that this as xp of n is equals to x of n between n1 to n2. We may write the equation as, so this turns out to be AK equals to 1 by n summation from n equals to n1 to n2, and this xp of n I'm replacing by x of n just because I want the equation for x of n, and remaining this exponential remains as it is, omega naught n. Now this term here, the summation term, I'm representing that term with some expression here. So I can write this as, say, x of k omega naught by n, where this capital X k omega naught is the term in the bracket. So this term in the bracket is nothing but this capital X of k omega naught. Now I can replace this term ak into this main equation, the synthesis equation. So what I obtained here is that, so if I take this equation, this equation is going to be xp of n equals to summation over a period of n, and this ak is capital X k omega naught by capital N times e power jk omega naught n. Now this equation here, that is xp of n, we are represented in terms of capital X k omega naught by n, and just because this capital N is constant, I may take it outside, and what we are left with is this capital X k omega naught times e power jk omega naught n. Let's observe at this expression here. Now, as we have seen that the aim of this module is to derive the Fourier representation for this discrete time signals, and this discrete time representation, or the Fourier representation of this aperiodic signal, that is x of n, we may see that this x of n is nothing but the part of xp of n having this n tending towards infinite. So let's impose this condition of n tending to infinite on the expression that we have just obtained. So now if we make this n, so if this n tend towards infinite, we may see that if this n tend towards infinite, this omega naught, that is 2 pi by n, tend towards 0. What do you mean by that? So let's observe this omega naught, the interpretation of this omega naught here. This xp of n is summation this k over a period of n, capital X of k omega naught e power jk omega naught n. Let's try to draw this expression here, capital X k omega naught e power j k omega naught n. So you may consider this to be something like a discrete time signal, that is a function of k omega naught. So if we try to visualize this expression, it would be something like this. We have that this capital X k omega naught times e power j k omega naught n turns out to be something like a discrete time signal whose consecutive samples are located with a distance of omega naught. As we may see that as k varies, k is an integer, so for every integer multiple of omega naught we would have a sample, that is x k omega naught, x of k omega naught times e power j k omega naught n. So what I have drawn it here is simply a visualization of x of k omega naught e power j k omega naught n, and we may see that individual samples, the two consecutive samples, are located at a distance of omega naught. Now if we make this n tending towards infinite, we would see that this omega naught tends towards 0. What do you mean by that is these samples are going to come closer and closer as this n tends towards infinite. So if that happens, these samples that are discrete in nature takes the shape of a continuum, just because something like this. So the samples are going to take the shape of a continuum. So discrete nature of this representation is going to take the nature of continuous variable. Why? Because this n is tending towards infinite, and if n tends towards infinite, this omega naught, that is the gap between two consecutive samples, is going to reduce towards 0. So if these two samples come closer and closer, close enough such that the samples are having no gap in between, so it would take a shape of a continuous variable. So let that continuous variable be small omega. So this small omega is, let it be k times omega naught, where when n tends to infinite, this omega naught tends to 0, and therefore this omega takes the shape of a continuous variable. Now let's see what happens with the equation here. This equation here, as you can see, as n tends to infinite, omega naught tends to 0, this x of k omega naught is going to take a shape of continuum, so it will become k of small omega naught and e power j small omega times n. So this is going to give you x p of n equals to capital X of omega, this continuous variable, times e power j omega n. Now just because this omega is continuous, this summation would go to an integration. So this summation would turn out to be an integration, just because this k times omega naught is now a small omega, and that is a continuous variable. Now we need to decide what would be the limits of that integration. So this is going to be an integration just because this omega is a continuous variable. Now this small omega, as we know, this small omega is nothing but k omega naught, and this exponential here is periodic with the period of 2 pi. Also we can see that this signal hence is going to be periodic with the help of this expression here. We can see that this exponential e power j k omega naught n is periodic with the period of 2 pi, just because this k omega naught is going to be omega. So this e power j omega n is going to be periodic, with period 2 pi, and we know that from the previous lecture, this complex exponential is having the period of 2 pi, just because this omega is a continuous variable here, and it repeats after a period of 2 pi. So this integration is going to be periodic or an integral of limit 2 pi. So this integration limits is going to be from minus pi to pi, or within any limit of 2 pi. Now we are left with this this capital N here. This capital N is nothing but this 2 pi by omega. You can see that is this N is nothing but 2 pi by omega naught, and we know that this omega naught is now continuous. So this N can be replaced as 2 pi by omega. So 1 upon 2 pi, I will take it outside, and just because this omega is very small, I'm going to write that as d omega. I'll once again repeat what I have said here. This xp of n is nothing but a summation of capital X k omega naught by n times e power j k omega naught n, and as we have imposed the condition of n tending towards infinite, We have imposed this condition because we want to obtain a periodic signal from a periodic signal. From this figure we can see that this aperiodic signal, that is x of n, is nothing but a part of xp of n when this n tends towards infinite. So we are imposing this condition of n tending towards infinite, and we observe that this omega naught tend towards 0 in that case, because omega naught is 2 pi by n. And if we visualize that with the help of this diagram, we can see that the two consecutive samples that are located at a distance of omega naught, this distance reduces as n tends towards infinite. This distance tends towards 0. If that distance tends towards 0, this takes the shape of a continuous signal, that is omega. Therefore, this summation here, the summation takes the shape of integration. So this summation passes to an integration here, and just because this k times omega naught turns out to be capital X of omega naught, x of k omega naught turns out to be capital X of omega naught. So you can see that here this capital X of k omega naught turns out to be capital X of omega, just because k omega we have considered it to be omega, simply replacing that, and this n, that is 2 pi by omega, we are replacing that with 2 pi by omega, just because this omega being very small, I am replacing that with d omega, and we would be obtaining the signals expression something like this. Now if this is going to be the expression for the xp of n that we have seen here, now as we can see that this signal xp of n as n tends towards infinite is going to be x of n. This is indeed the expression for x of n. So I'll write the expression x of n is going to be 1 upon 2 pi integration over a period of 2 pi capital X of omega e power j omega and d omega, where this capital X of omega is given by summation. You can see that we have defined this as capital X of k omega naught, this term here capital X of k omega naught, as the summation x of n e power minus j k omega naught n. Now this limits n1 to n2. We can now take a generalized limit from minus infinite to infinite, just because this x of n is 0 otherwise. So what I mean to say is that this signal x of n, as it is defined between n1 to n2, we may consider this to be defined from minus infinite to infinite, where the other samples are 0. So it doesn't matter what limit we take. So as it is defined from n1 to n2, I may take from minus infinite to infinite as well, just because the other samples are 0. So in general, the expression would be this n from minus infinite to infinite, x of n e power minus j omega n. Why omega? Because we have seen that this k omega is going to be continuous variable, that is going to be omega. So we have obtained here a new set of equations, and this we called it as a discrete-time Fourier transform, or the Fourier transform representation for discrete time signals. So this is the Fourier transform of discrete time signals. Let's stop here.